Yeah, so the next speaker is Brittany Schmidt, and she will talk about landslides on Ceres, reveal hidden ice. So let's start.
All right, everyone, time for something a little bit different. So I'll be telling you a bit about our work on the geomorphology of Ceres' surface and what that might be telling us also about the subsurface. So rather than talking about the very shallow surface, as we've been talking here for a while, we're going to talk about the deeper subsurface. So perhaps one of the surprises of the mission has been that one of the dominant surface processes on Ceres is in fact landslides or mass motions of a variety of kinds. So I'm just showing a survey here of a bunch of different styles of landslides that we see. You saw Juling crater a little bit earlier. I think this is one of these should be, there's an early picture of Juling crater as well, Oxo, a few others on here. So we have all kinds of different styles of mass motions. They have different properties, and so we've been kind of characterizing how these different features operate. We have examples of really spectacular landslides as well, so things that we don't see on many other planetary bodies. So this is my favorite one. This is from a crater around 80 degrees north. You can see this big, huge landslide motion here. It's about 300 meters thick down here at the toe, for example. This is another example of one. So while all of the landslides that we see are associated with impact craters, it's probably because that's the source of topography on Ceres. So we have a variety of very simple landslides and then things like this that are more complex, where we have multiple different events, multiple different lobes, and probably different generations of landslide motion, or at least potentially. Some are similar in age to the crater, and some are very different. And then we have much larger landslides, such as this one here. This is what we call a type 3 landslide. I'll discuss those types here in a moment. But in this crater, we actually see kind of a very fluidized lobelet structures here that extend pretty far from the crater wall to the exterior of the crater. So the association of the inside and the outside of the crater is also important. And this is just showing that in addition to this large massive slide here, we have mass wasting towards the center of that crater as well. So how do we start judging this planet, at least by its cover? And by this I mean the upper tens to hundreds of meters. So we're going to talk a little bit about the geomorphological characterizations that we've put in place. And this is from a paper that came out earlier this year. So we've classified all of the landslides that we have into subcategories, very creatively named type 1, 2, and 3. So this is a type 1 landslide. So this is the one that I just showed before. So this is kind of our classic, what we call a tongue-shaped or lobate flow. What you can see is that the material originates at the crater rim. So here we've got an older crater rim with material that's actually sliding down the surface, down the interior crater wall from an additional source crater up here. So we think is perhaps that the impact into this event allows this material to become unstable. Sometime later it's triggered and flows down into the larger crater. Characteristics of this is that you have levees or moraines or structures to the outside of some of these landslides. That you have tens to hundreds of meter thick toes that are very robust, so they are kind of steep fronted. And in many cases we have transverse furrows that run along the direction of the flow. So these are relatively, transverse that can kind of cut across the flow, and then parallel furrows that run in the direction of the landslide motion. So these are the most voluminous features. If we go to type 2, these are a little bit thinner. They're very similar in shape. They still kind of have a rounded nature, a lobate type structure. However, they're much more thin. So we call these kind of spatulate sheeted flows. So they still have that rounded edge, but they're much thinner. They're generally along shallower topography. They're also characterized by generally shallow failure scarps, which we'll discuss here in a bit. and relatively smooth. They lack a lot of the furrowing that we see in the type 1. And so these run out fairly long distances despite the relatively short or relatively smooth topography. And type 3 landslides, we're still calling them landslides here because they're not completely circumferential to the impact craters that source them. In some cases, they can go up to about, between 90 and 180 degrees around the crater. But in this case, for instance, we've just got a flow in one direction. These are more highly fluidized. They tend to flow longer and be more cuspate, so they have more acute toes at the terminus. So these are really, really thin. They're reminiscent of fluidized ejecta that we see on other bodies. And so that's how we classified them according to geomorphology. This is where we find these features in general. So the blue dots here are the type 1 landslides, those thicker lobate ones. Type 2 are the kind of spatulate sheeted flows. We find those actually kind of all over the surface. And type 3 are these features here, mostly in the mid-latitudes or low latitudes. If we look at that in terms of aerial distribution, so this is the percentage of the flow that covers any given area, this actually reveals what you can kind of see in this plot, which is that while we find type 2 flows across the surface of Ceres, we have very rare occurrences of what we're calling type 3 or fluidized flows. We see a real trend of a high presence of these type 1 flows up near the polar latitudes. So at high latitudes, we find these kind of thicker, voluminous flows. We find the thin sheeted flows kind of everywhere. And then in special cases, we find fluidized flows. So that's kind of how these break out according to geomorphology. So what we've been doing, and that was kind of the work that was presented in our 2017 paper by the Ground Ice Working Group from Dawn. So what we've been doing to follow up on that is to look at a second way of categorizing the material, which is according to mobility, which we started in that paper, but really also looking at failure mechanics to see if we can tell something else about the subsurface from these landslides. So the way this works is that you can actually use the landslide geometry to tell yourself something about the physics that the landslide is going through as it forms. We're going to focus first on the mobility, so we're looking at the properties of the deposit, so the action that it's experienced. So we have a simple friction model that basically relates the friction inside the flow to its height and length. So essentially how the kinetic energy transitioned from falling becomes kinetic energy of motion and how that affects the landslide. So we can measure from the farthest point on the source crater all the way out to the farthest point of the toe, and that gives us our maximum measurement. If we wanted to be a bit more conservative or describe the flow as a continuous material, then we'd want to look at the center of mass of the material and kind of estimate that based on its topography. Obviously, it's much easier to measure the maximum runouts, and those are the standard procedure in planetary landslides, just given the resolution of the images and topography that we have. But we've gone through and compared both measurements for Ceres landslides. So here's for all three from the first paper. You can see that there really is a correlation here where we've got clustering of most of the type 1s up towards these higher values of internal coefficient of friction. We've got both type 2 and type 3s kind of lower down here. But the important thing to note is that there really isn't a trend for those type 3 landslides. And that's what you expect if the sliding friction is being overcome by fluidization, or if the flow itself is somewhat internally fluidized. There's other things that can happen. It could be acoustic fluidization. We prefer probably grain boundary sliding with ice or liquids in the flow based on several factors. But basically, these type 3 landslides really are very different and probably associated with impact melt. But type 1s and type 2s are kind of clustering differently. This is just a quick comparison to the behavior of landslides on Earth and Mars. Generally, Ceres is a little bit more shallow, so a little bit more mobile than flows that we see on both Earth and Mars. For the analysis that we've been doing most recently, what we've gone back and done is looked at the very end member sets. So the hundreds of landslides I just showed you characterized, they're really a continuum. We have really extreme examples on one end and on the other, and then in the middle we have a whole bunch of stuff that kind of shares those properties. So what we've done here is to go back and look just at type 1 and type 2, since those are more landslide type behaviors, and we've looked at a restricted set of them that represent really good end member cases, to try to isolate what the difference is or the physical difference between these might be. So on the left here, this is both the maximum values in the open dots here, and in the stars, these are the center of mass values for the type 1 flows and for the type 2 flows. And so it kind of shows that there's a little bit of an upward trend here for the type 1 flows that we're looking at, and a little bit of a lower value for the type 2s. And what we're plotting here is the values of laboratory measured coefficients of friction for different materials. So ice at 233 Kelvin, ice near 273 Kelvin, dry clays in here, wet clays out in here. So these are all Ceres relevant materials. So the physical properties of those measured in the lab compared to what we're seeing from the landslides. So in addition, all of this work here has focused on the mobility of the deposit. So what is the deposit telling us about the physics of the landslide emplacement? So if we instead wanted to look at how the failure occurs in the first place, that's what gives us a little bit more information and insight into the structure or the layering of the subsurface. So in terrestrial landslides, it's been observed that there's a difference, a statistical difference between soil type or shallower landslides and bedrock type or deeper failing landslides. And so those are observed in the field, and they give kind of two different values of this parameter called gamma. And what gamma does is it relates the volume of the volume of the landslide scar to its own area. And so it gives us a physical separation of different types of landslides. For Ceres, we actually don't have a really good way of estimating the volume of the scar. We can easily estimate the surface area of the scar, but what we have to do here is to usually use the volume of the deposit as a proxy for the volume of the failure scarp. So this is approximately the scar value. Obviously, it's a little bit of an underestimate because we don't have great resolution on our DTM, and we result in using the volume of the deposit actually will overestimate what the original volume of the scar was because you're entraining material as you go down the side of the crater. But it gives us at least some kind of a constraint. And so we kind of take this whole area that we call the preferred area, which is all of the failures that we can see related to that landslide, and then compute these using this area and the volume of the deposit. This is just kind of showing the way that the terrestrial landslides kind of plot out, where soil landslides generally cluster down here at a lower value, and then these bedrock landslides are at what's called a self-similar scaling, basically of 1.5. So where does Ceres line up? These type 2, we see an actual split in the behavior of the type 1 and type 2s. So it looks like the type 2s are kind of a deeper failure, which might imply a more continuous or coherent material, whereas the shallow, or the type 2 landslides look a little bit more like kind of shallow failures, implying perhaps a layered or looser material. And these are the terrestrial, bedrock, and soil values for comparison. So why is this important? Why do we even care about what the landslides are doing? Well, let's go through a quick thought experiment. We have all of this evidence that we've got ammoniated and hydrated phyllosilicates. We've got some water ice, but it's unstable on the surface. We've got this increase in water equivalent hydrogen towards the poles, and then this behavior of landslides that seems to be different across the surface. So if we want to learn about the subsurface, at least below what Grand and Veer can see, so let's assume either option 1, which is that the surface composition is relatively homogeneous. So we have a material with variable hydrogen content and perhaps increased strength or cohesion at colder temperatures or near the poles. Or option 2, perhaps the surface composition or the subsurface composition is a mixture where you have a second material with higher hydrogen content that's below that. So what are some possibilities for that match our observations? One of the really interesting things to think about might be to think about smectites. So it's a type of clay that as it thermally cycles can actually produce ice lensing. So if you imagine impacting into these clays over time, heating and then freezing them out again, there's an opportunity to create mobility of water from this variable amount of water that's inside the matrix of the clay. In the second option, you have kind of a serpentine or a smectite mixed with ice, and then this ice is actually doing some of the work to bond the materials together. So somewhere in the middle is maybe where we have this. The reason that the landslides are pretty interesting is that we see basically that we have soil failures in the lower latitudes and perhaps bedrock failures towards the poles, which might correspond with this idea that there's a buried ice table as presented in Grand and as is evidenced by the different landslide mechanics, both from the failure perspective and from the deposit mechanics. So what we think is perhaps you've got a layer of kind of thermally cycled clays in the upper tens of meters, maybe 100 meters, and then deeper, an ice-rich table that's cementing the materials together. So if we take all of the dynamics of the landslides together with the composition data, we think we have a pretty good story that the thermal cycling or the types of clays that we see might be why we have this globally distributed type 2 landslides, but we have the type 1s at the poles that are more related to actually ice failing all the way to depth. It matches some of the Grand data, makes sense with the surface composition. So that's kind of what we're thinking. So I'll leave it there.